All right, good afternoon, everyone. It's my great pleasure to be here today to share my innovative endeavors, ADIF and PIAAR ratio projects, all of which are based on geometric framework to maximize the efficiency of guided implant surgery. And to begin the lecture, the conflict of interest, I have no financial disclosure, no sponsorship, and hope you enjoy it. So we are living in the era of technical innovations and advancements. Got so privileged in alignment of our generation of waves of progressive innovations, and the computational intelligence especially. We do have the coding systems, the NVIDIA chips available, all of which all these AI mathematical and algorithmic models are truly actualized. And we're looking at the trajectory of our plan, where we are going as a compiling all these available resources to projectile into the meaningful journey with the shared mission, vision, and philosophy. So I'm from New York. Here's the view from the Midtown. Truly enjoyed the geometrics, and we'll see the reason why. I love the foundation of geometrics. I love the trigonometry, the mathematics, and that's probably the foundation of my research that I'll show you the patent applications and innovative activities through these. Perhaps that's why I became prosthodontist. I love preparations. I love aesthetic transitions, and how I apply these geometric trajectories into my clinical arenas. And as a surgically practicing prosthodontist, I also in private practice and academic setting where I'm leading the robotic surgical program. And I truly feel privileged with a genuine passion in what I do. And as an academician and a clinician, I've been pursuing these for future generations as well. I love teaching, and I really feel privileged to impact the next generations as well. And particularly, I love innovations. Back in Boston, I served as co-founder and the chief science officer. We developed these mixed reality neurosurgical dynamic navigation system, which is now FDA cleared, and I truly love innovations. That's why I immerse these innovative initiatives into my subspecialized expertise of full arch implant reconstructions. As you can see, I truly love geometrics that try to make these workflows in full arch rehab as a more predictable, conservative, and efficient. And here's a recent publication with International Periodontist and Respiratory Dentistry, where I tried to sort of narrate these geometric foundation through the full arch reconstruction and implant. With some innovations with the retyping bilateral sling parastomator sutures and pacification and mechanical transduction-induced GBR. And as you can see, I love innovations. And in the field of full arch implant reconstructions, as you know, we have so much foundation and technical advancement should be necessary to pursue these type of accurate and precise matter. With your initiative of mode, high quality, craftsmanship-driven treatment philosophy. Particularly in computer-assisted implant surgery, if you see, as a patient perspective, it's been so advanced that we decrease the clinical chair time and efficiency as well. As a clinician perspective, we put X amount of time to pre-plan these before the surgery. And that's where these challenges I would like to address. When you're positioning these implants, such a requiring fatigue and cognitive burden. And therefore, it may use some manpower and training, a potential business inefficiency sometimes. And out of all, the lack of objective technical quality control, meaning whoever is doing implant planning, we're so relying on our subjective philosophy into it. There's no pre-existing assessment of parameters, which implant position is ideal implant position. And that's where we had some changes. We have the static surgical guide, dynamic surgical guide, and now haptic robotic surgical guides. And now we have such advanced like VR, augmented realities, all of which we are creating these surgical executions as simple as possible. So it's become more efficient, more quicker and simpler. And if you pursuing these implant surgeries, you can appreciate that it's getting more efficient and practical. All of which become chances of how we can put these biomechanical views into the surgical arena. And here's the clinical example where we pursue the robotic surgery, where the patient had a distal extension where there's no denture, pre-existing denture as a blueprint. So we had to do it as a chairside dental wax up, as a chairside. And as you can see, I put the quick blue bite with the flowable composite, which is radiopaque, all of which we get the vertical reference. So when you do the digital wax up, it becomes more predictable and more reliant for the surgical execution, even pre-planning phase. And that, I'd like to emphasize, a prosthetically driven implant surgery. And these surgical innovations, we have emerging opportunity for chances in prosthetically driven implant surgeries. And that's where this PIAAR ratio comes in. Has been originated by my continuous skepticism and our current biomechanical understanding of full arch cantilevers. If you look into the pre-existing data, it's really relying on the linear ratio, or 1 to 1.5 ratios. But if you see closely, there's so much heterogenic potential. Everybody has a different arch forms, different implant locations, implant numbers. The locations are not the same, the prosthetic contours are not the same. The cantilever is not just posterior. We have anterior, lateral cantilevers as well. So that's where I put these mathematical ratios, the Hermann's formula, which is based on the Pythagorean concept. If you know the 3 known values, you can calculate the area. And that's what I did. What I did here is I came up with a system where you can create the multiple triangles, and then you can get the area of the prosthetics, and then the implant arch area ratio as well. And this becomes a system that we can create this mathematical ratio, a bit more categorized for our further biomechanical studies. So following the power analysis, I collected 15 casts and applied this PIAAR allocations. And as you can see, I designated these consistent vertical 1 to 1.5 ratio with different horizontal expansion of it, in a way to pursue these statistical analysis to justify that this categorization system is a bit more comprehensive, more geometric categorized, and then the perceptive modality. But we can pursue these biomechanical studies with these categorization systems. And branch from the full arch, we realized we can apply the single units. We have different implant diameters, we have different crown portions, and we can apply the same ratio into single unit implants. And that's what we did here. We allocate the central position of the implant fixture by angling it in the minor fashion to minimize the confounding factors. We fused the implant fixture with the abutment together, and then we allocated the trabecular cortical bone. And we run the FEA finite element analysis as a simulation. We saw how it goes, and the different access hole positions. And then we allocate the exact same occlusal view with the same morphological appearance of the occlusal view, in a way that we can come up with this PIAAR ratio with the different anterior, posterior, buccolingual positions. And we apply the centric and eccentric forces. As you can see, the 4 quadrants of the centric occlusion, and the 2 as 30 degrees as a non-eccentric convex. And looking at the deformation of these implant to abutment fused fixture per se, when we run the FEA study, we pursue the maximum deformation of micropascals in a way that we can come up with the numerical data. And interestingly, even with the singular matrix investigation, we got some meaningful results. As you can see, the eccentric occlusion and the buccolingual variations, they cause more heterogenic appearances. And then what we can get out of these as a clinical implication will be patients with more worn down teeth or functional groove functioning, that we should be a little more careful for the buccolingual allocation of the access holes. So these type of matrices, as you can see, we are seeing some patterns here. If you look at the left corner, we do see the symmetric appearances. What does that mean? We can apply the Gaussian model, the normalization of it. And once we have such patterns, we can apply this Gaussian distribution. We can come up with the equations. The mathematical equations becomes possible. The issue is the heterogenic appearances, as you can see the eccentric context here. And that's where it becomes a bit more complex orchestrations. And when we investigate these heterogenic appearances of eccentric context, we are applying this complexity of instability of these appearances as a characterization forms and geometric invariance. And when we further investigate, we realize these confounding factors, they become inevitable biomechanical factors. that we should put it in, and not only the PIAAR ratio, but we should combine all these occlusal biomechanical factors to understand what's the real representation of the patient occlusal situation, which is the Hanauer-Quint or Thalmann's formula, well known to be for the balanced occlusion. We are trying to create this matrix development through modifying these Hanauer-Quint, the Thalmann's formula. As you all know, the AI technology has been already begun. It's conspicuously the fourth industrial revolution. It's no longer a question whether we utilize it or not, but it's rather strategically position ourselves how we can utilize them. Here's an example. So as you can see, the dental maxillofacial radiology, the journal, ever since 2019, 70% of the most cited articles AI related. And it is with us already, especially the diagnostic phase. The issue is the full automation is still yet unavailable. And why is that so? And if you think about these artificial intelligence, we need to dissect into how the artificial intelligence is narrated. As you can see, the artificial intelligence, performing tasks of the human intelligence. We have machine learning, which is a subset of AI, and we're learning patterns and improving the performance. And we have a deep learning, which is a subset of machine learning. And we are utilizing these multi-layer artificial neural networks with a high level of acquisitions and abstractions. And now I want to focus on this deep learning. Well, what do we have in the deep learning? As I mentioned, it's based on the human neural networks. And the first dental article is periodontal detections. How we're applying these periodontal deteriorations, how we can predict them. Using the same neural network concept, we now actualize these segmentation of the CBCT acquisitions, how we can make these segmentation more efficiently. And also the allocation of the edential sites, and how we can detect the teeth or edential sites. And now translating into the next phase of the deep learning, the denoising diffusion probabilistic models, where they're utilizing these mathematical model to make our acquired CT scan more accurate and precise. Because as you know, we have a crown or denoising factors, and they're applying these deep learning model to make our CT scan more accurate. And then of course we have language models, well known to be the ChatGPT, Gemini, or Copilot. We're applying these into the dental community as well. Now we're actualizing the differential diagnosis, the treatment executions, how we can narrate this treatment planning generations. And now, all these advancements, we need to sort of step back and think about it. Because in the deep learning and generative AI, if we are lacking the post-treatment as a data bank, it sort of becomes meaningless. So that's where I'm proposing as a strategic appearance of the position with this project, the ADIF project, how we can strategically position ourselves. So here's the ADIF team. I'm very proud and privileged to introduce our team here. The NYU Dean's Faculty Research Funded, and that we progressed and presented the inaugural AI for Science Research Conference at NYU, the New York City. And the system itself is quite simple. We acquire the data, and then we start visualizing and planning the implant fixture and diameter of it, and we pursue the surgical execution. And we're utilizing the storage bucket of the generative AI division from NYU, and then we are compiling these data sets, and then we can actualize the plan. And we start with the NNUNet segmentation, which is originated by Dr. Guthrie Dodd, which is open source available, the code. If you're interested, you can explore that. The bottom line is we're actualizing the CT scan image into an STL file conversion, and then we can visualize them into our platform. And in this case, we utilize it for site detection. We can detect the edential site and all the tooth numerical allocations and the edentulous detection. And interestingly, we found the Gaussian normal distribution here as well. If you think about the general location of angulation of the tooth, we have a generalized the location of the tooth itself. The detection of the molars is close to sinus or close to nerve. We create these Gaussian models. We can create these normalization, and then we can come up with this equational matrix system. And we pursue this multi-dimensional scaling. Basically means once we detect the site, we sort of fine-tune the site for preparing our implant selection and the length allocation as well. And here's our deterministic algorithms. It's under the IP where we are creating this sequential algorithm that once we detect the site, we follow this algorithm, that we can create this site detection with the slicing with the bone dimension. And here's the next version of the deterministic algorithm that once we detect the site, we can slice it. That's exactly what we do when we plan to implant a plan. And we call it JCL planning algorithm. And then once we have these sections, the implant selection and the diameter become uneventful. And following these IP patent applications, our initial goal or ultimate vision is to release this software as a plugin module to pre-existing dental softwares in a way that we can apply this no-fee registration. And the one requirement is putting the post-surgical CBCT in a way to the encryption and then the cloud-based system. We can actualize this data bank, and then we can accumulate these data. And as I show you, the machine learning and deep learning can be now applied with these post-surgical data bank. And here's my last slide. The previous innovation in healthcare has been led by the medicine. It's due to the drastic scope of its profession itself. And I humbly believe this is time point where the execution of AI-driven treatment will be led by dentistry, given its highly subspecialized and clinically focused nature and its robust potential of algorithmic treatment executions and trackable data banks. Two of the key factors of machine and deep learning. So for the sake of today's lecture, I couldn't go too detailed, but hopefully you enjoyed the innovative perspective of this lecture. And if this lecture has resonated with you, please feel free to contact me through the below barcodes. Thank you very much.
Any questions? All right, I have one.
Yes.
So if you're going to use the auto distribution of implant fixtures in the arch area ratio, and those are sort of the inputs, and you're talking about this sort of post-surgical data bank. So if you're able to use the ADIF and the PIAAR to, in your mind, optimize these surgeries, tell me a little bit about what the outcome data looks like in terms of, how the system works. How do you assess the validity of your system?
That's a very good question. That's my very first question when I came up with this concept. So we are planning to, once we actualize this data software, we're going to release to institutional settings. And then we're going to acquire the first case scenarios. And then we're going to put the expert surveys. And then in a way that we compare the AI, the PIAAR ratio, or the ADIF generated implant planning versus the clinical expert planning. And then we're going to get the survey to start with. And then to answer the question, the objective matter is still missing. So that's why I'm pursuing simultaneously the PIAAR ratio to come up with the biomechanical matrix system. So we can idealize what's the ideal range of the implant planning. How much angulation? If you're angling buccolingually, what is the ideal range? And that's where the multiple factors come in. I realized through my own investigation, it's not just PIAAR ratio. It combines multifactorial issues. The height of the crown, implant diameter, all these matters, they matter. So we're planning to include all those factors together as a comprehensive biomechanical matrix system. And by the time we have them, then we can have more systematic the assessment toolkit, pretty much, to evaluate our implant is ideal or not. And second route is the post-surgical CBCT import. And that's important because we would like to see how these angulation of implant, biomechanically and surgically, they've been successful. Of course, if we look at the limited number of cases, it looks quite vague. But if you look at the multi-institutional and then the number of increased cases, like a million cases, then it becomes a really accurate, sophisticated matter. And that's where, even with our initial investigation, we came up with the clinical implication. The more data we get, it's become more comprehensive. So that's the beauty of this technique, the strategy that we're putting in. We're going to acquire as many data as possible, not only the executional data, but also the post-treatment data, and we keep following up. We pack that as a data bank. And then we can see which cases have failed or not, which cases we had the fracture, immediate fracture, or the near fracture, like the biomechanical fractures, and we can compile it together.
What's the difference between executional data and post-treatment or post-surgical data?
So executional data could be based on the initial PIAAR ratio, like some of the biomechanical, the planning. What's the ideal, the position of the implant, in reference to the crown prosthetics. It could be implying the shape of the morphology too, like whether it's the monoplane anatomical, and we get the initial data, and then the post-treatment data will be purely based on prognosis. And we do have some of the literatures, we have systematic reviews, but we're going to rely more on the real clinical data bank. And that's where we're missing. That's why I put that as a puzzle, because we do have those knowledge, we have systematic reviews, we have all those resources, literatures, but we are really lacking the daily real clinical matter. But what's the real implant failure rate, that kind of stuff. We can put it in the real patient data into the system, and then we can compile them. Yes?
I have one question. Very interesting. Did you use finite element analysis for your training, your data model?
Yes, yeah, we use a data model for the PIAAR ratio, yeah.
And maxilla versus mandible, did you use different Young's modulus for the bone?
Oh, so we
compare those two?
Right, yeah, so on the FEA studies, if you know the ASIS software, they have the real clinical implication to it. So as of now, we run the molar on the mandibular number 19 site, and that's the starting point. And then, as you mentioned, the maxilla versus mandible, they have different dimensional informations, and we can put further data into it. And later we can put whether the GBR or simultaneous GBR condition, all those conditions can be pre-added. And as of now, we start with the most simple 19 missing site, and then we can apply these matrices in addition to that. Immediate extraction, immediate placement, all those things can be added into it.
I mean, something like this is very common in engineering. They use generational design. So those are very commonly used. This is basically a derivative of that.
Yeah.
You should take a look at that.
Absolutely.
There's a lot of information on
So our goal was to make it as simple as possible for the beginning of number 19 site. And then, of course, we can add on top of it. Yeah.
Really interesting presentation.
Thank you.
One of the things you really talk about the access hole and the actual angulation. Like, is the program going to be designed to actually accommodate for occlusal morphology changes, especially because you're talking about off-axis loading or extrusive movements?
Yes.
Is it actually going to put that plan into the final restoration?
That's true. So we're putting the centric and eccentric forces purely for analyzing the access hole positions. That's what I mentioned, the confounding factors. But if you think about the angulation of it, that's pretty much the only variable we can put it in to actualize different access hole with the exact same implant crown morphology and exact same implant fixture. So that itself is a confounding factor. That's why we put the centric location of the implant fixture as a vertical reference so that we don't have any fluctuation of it. We try to fix it as much as we can, and then that becomes our confounding factor. And then once we have this data, as I mentioned, we're planning to compile more comprehensive matrix system, and then each model will be added. And then right now, this is the very simple version, initial version of it. And then we can add the morphology, as you mentioned, anatomical, the monoplane, implant diameters, and then the location of implant, how subcrustal, 1 millimeter, 2 millimeter, 3 millimeter, and then we can put all these comprehensive data. The issue is the initiation of it. Once we have those as a matrix system, then we can compile these data. Even these 6 samples of the FEA, we get something out of it. Imagine we have 10 million data with the different variables. It's going to be really comprehensive, and that would be the true blueprint for our biomechanical understanding of it.
Excellent. And then just one other question. How many samples do you think you need before it's actually considered an accurate sample?
Right, so
you're talking a million and 2 million.
It's a bit more philosophical question. Yeah. If you look at all those literature references that I put in, every study has their different data bank. Some studies, they really gain a lot of data, whereas some clinicians, like they have only 3,000 slices. So you really, at this moment, we don't have a finite answer. But the bottom line is we're creating these systems, and then we're open-minded to get those matrix systems as collections. Yeah. So thank you for your question.
Thank you.